Hey guys, today we are going to talk about the complex zeros of a polynomial function. So first thing we're going to kind of talk about what our different types of numbers are so we can kind of remember what complex numbers are. So the first type of numbers are the natural numbers. The natural numbers start at 1 and they're the numbers that we count by. So 1, 2, 3, 4, 5, so on and so forth. Then our next set of numbers are our whole numbers. And so they're all the natural numbers, but the difference here is that now we include 0. So for a long time, 0 wasn't actually a number because numbers started off by being counting numbers. And if you don't have anything, you don't need to count it. So we started at 1. Then 0 became a number as a placeholder, so you would know the difference between 11 and 101. And then it's finally got its own spot on the number line. And so then we get up to whole numbers. So as we're going from like cavemen and progressing and, becoming like farmers and things like that and growing our own food. And then we keep progressing. And as society keeps progressing, we start to get into negative numbers and we get into the integers. So our integers include the negative numbers, 0, and our positive numbers. And then society is still progressing, and we get into rational numbers. Rational numbers is where we start getting into our fractions. So we have p divided by q, where p and q are integers. So anything that could be written as a fraction, where the top and the bottom of the fraction are both integers. And if it's not a rational number, the other option is that it can be an irrational number, which is any number that cannot be written as p over q, where p and q are both integers. So a really famous example of an irrational number is pi. 3.14, the big long decimal, cannot be written as a fraction where the top and bottom are both integers, so that's an irrational number. Another one is e. You could think about the square root of 2, but remember another example could be like the square root of 2 over 4 or pi over 3 because those are fractions, but the top of the fractions are not integers, so those are irrational numbers. So don't just assume that because it's a fraction, it's a rational number. Be careful with that. Then our rational numbers and our irrational numbers together make up our number line, which is what we call the real numbers. And that's what we're used to working with. That's what we talk about in Algebra 1 and Algebra 2 and spend a lot of time with our real numbers. They make up the number line. It's a complete number line. Every single part of the number line is filled in with either a rational number or an irrational number. Now, what we're going to add on today are our complex numbers. Our complex numbers is where we get I. So remember, I is the square root of -1. And our complex numbers are the form of a plus bi, where a and b are real numbers, but then we put that I in, which is what makes it a complex number. So you'll notice that all of our number systems are kind of nested into each other. So a natural number can be a whole number. Ooh, let's get the pen, not the highlighter. A whole number can be an integer. An integer can be a rational number. A rational number can be a real number, and then real numbers can be complex numbers. So real numbers are technically part of the complex numbers. So normally we think about complex numbers being like 4 plus 9i or 6 minus 12i, but technically we could also write it as like 5 minus 0i, and that 5 is a real number. And then the 0i part, remember, if it's 0, it's just 0. So it's technically just a real number, but it's part of the complex numbers still. So just kind of keep that in mind as we're going through today. Then we've got two theorems. The fundamental theorem of algebra says that every complex polynomial function f of degree n greater than or equal to 1 has at least one complex zero. So a polynomial function of degree n has exactly n roots, is kind of the easier way to say that. So a polynomial function of degree n, so like degree 5, is going to have n roots, so 5 roots. Degree 12 would have 12 roots. Degree 27 would have 27 roots. So whatever the degree is, that's how many roots you have. So what it looks like let's look at our quadratic. The quadratic is x squared. So let's draw a graph. If we're looking at quadratics, if it's x squared, the degree is 2, so we should have 2 roots. So the most common thing we look at is it touches in 2 places. There's our 2 roots. Another option is that we could have our quadratic and it only touches in one place. It kind of bounces off the axis. So let's say that it touches over here at 5. Remember, if it bounces, we talk about roots having multiplicity. If it bounces like that, it means it has a multiplicity of 2. So we could write this as x minus 5 squared, which would be the same thing as x minus 5 times x minus 5. So even though it only touches once, that root has a multiplicity of 2. So it's the same thing twice. So technically we do have 2 answers. It's just the same answer twice. And then the other option, which is kind of what we're going to look at today, is what if it doesn't touch at all? So what if over here on the right, because I ran out of room on the left, I've got a quadratic that doesn't touch my x-axis at all, and that's where we would have 2 complex roots, 2 complex zeros. So also remember roots, zeros, x-intercept solutions, those all mean the same thing. So we would have 2 complex answers. So that's our options. Kind of an example there for you. The other thing to know about our complex answers is the conjugate pairs theorem. It says let f be a polynomial function whose coefficients are real numbers if r equals a plus bi is a zero of our function, then the complex conjugate a minus bi is also a zero of the function. So our complex answers come in pairs. Specifically, conjugate pairs, a plus bi and a minus bi. So the nice thing about that is that whenever you know you have a complex zero, you know you got at least 2 of them. They're always going to come in pairs. You're always going to have an even number of complex zeros. So let's look at some examples and see what this looks like. So we're going to start off a little bit easier with a quadratic. We've got x squared plus 4x plus 5. So you've got 2 options here. You can use your quadratic formula or you can complete the square. So let's use our quadratic formula. So remember, if we've got ax squared plus bx plus c, my quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So I'm just going to take my a, my b, and my c, and I'm going to plug it all in. So x equals negative b would be negative 4 plus or minus square root. B squared would be 4 squared minus 4 times a is 1 times c is 5, and it's all over 2 times a, which is 1. We can start cleaning it up a little bit. So x equals negative 4 plus or minus the square root of 4 squared is 16 minus 4 times 1 times 5 is 20. 16 minus 20 is negative 4, and it's all over 2. And this negative 4 right here, that's where we're going to run into some trouble. Square root of a negative 4 is where our complex answers are going to come into play, our complex solutions. Square root of a negative number is how we get complex numbers. So what you do is anytime you have a negative number, you're going to bring the negative out and make it an I. So I'm going to have x is equal to negative 4 plus or minus I square root of 4 all over 2. And then I'm just going to solve it like I normally would. So bring the negative out, make it an I, and then solve it like you normally would. So in this case, it's a nice, pretty, perfect square. So I can just figure out what that square root is. But if it wasn't a nice, pretty perfect square, you would need to break down that square root like you did back in geometry. So the square root of 4 is just 2. So I can come and write this as x equals -4 plus or minus 2i all over 2. Then the last thing I need to do from here is actually divide. If I have -4 plus or minus 2i, both of those can be divided by 2. So I would go ahead and write it as x equals -2 plus or minus I. -4 divided by 2 is -2, and 2i divided by 2 is just I. Okay, you can leave it like this with the plus or minus combined. Ooh. Or if the plus or minus option isn't there in my math lab, you could write it as -2 minus I and -2 plus I. So you can leave it together or you could separate it. Okay, let's step it up a little bit. Let's look at one that's not as easy as a quadratic. Let's look at one that's got a fourth degree. So for this one, we've got 3x to the fourth plus 5x cubed plus 25x squared plus 45x minus 18. So when we've got an x to the fourth like this, we need to go through and do our p's and q's and do our synthetic division. So I'm going to start in the back with my p's, my 18. So I'm going to see what can I multiply to get to 18. So I've got 1 and 18, 2 and 9, and 3 and 6. Okay, and then I'm going to go back to my q's. I've got 3. And so to multiply to get 3, I've got 1 and 3. Okay, so I'm going to take all of my p's and divide them by my q's. So I'm going to start with dividing by 1. Dividing by 1 is nice and easy because dividing by 1 is just going to be the same thing. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18. Okay, and then I'm going to divide by 3. So when I divide by 3, I'm going to have plus or minus 1/3, plus or minus 2/3. 3 divided by 3 is 1, which is already in my list. 6 divided by 3 is 2, already in my list. 9 divided by 3 is 3, and 18 divided by 3 is 6. So when I'm looking at this, now I've got to figure out what I'm going to use to divide by. So you've got a bunch of different options here. You're going to pick numbers from that list. And so I've already done the problem. I'm going to save us a little bit of time, and I'm going to try -2. Okay, if I pick -2, that's going to go in my box. Then listed out next to it is going to be 3, 5, 25, 45, and -18. Bring down the 3. 3 times -2 is -6. 5 and -6 is -1. Then I get 2, so 27. 27 times -2 is -54. Then I get -9 times -2 is 18. And then I get 0. So that one works. I know x equals -2 is one of my answers. So if I know that that's one of my answers, then I also know that one of my parentheses is going to be x plus 2. Okay, then from here, I also know that I have 3x cubed minus x squared plus 27x minus 9. If I started with an x to the fourth, then when I do my synthetic division, my answer is now x cubed. And from here, I can actually go ahead and factor. So I can take out from the front group and the back group, so factoring by grouping. From the front group, I can take out an x squared, and I'm left with 3x minus 1. From the back group, I can take out a 9, and I'm left with 3x minus 1. So I get x squared plus 9 and 3x minus 1. And then I set both of those equal to 0 and solve. So if I have the 3x minus 1, when I set that equal to 0, I'm going to add 1 to both sides. So 3x equals 1. And then divide by 3, and I get x equals 1/3. So I can come over here and say x equals 1/3 is another one of my answers. And the parentheses that would go with that is the 3x minus 1 for when it comes time to write it in factored form. Then I have x squared plus 9. So I'm going to solve that. I'm going to do it over here. X squared plus 9 equals 0. I'm going to subtract 9 from both sides. So I have x squared equals negative 9. And when I take the square root of both sides, this is where once again I have a square root of a negative number. So I got to make sure that I bring that negative out. X squared is going to equal, and since I'm taking that negative square root right there, I've got to make sure I've got the plus or minus with it. So it's going to be plus or minus an I and a square root of 9, just like we had plus or minus back here with our quadratic formula. And the square root of 9 is 3, so it's just going to be x is equal to plus or minus 3i. So my last answers, technically it's two answers, up here would be x is equal to 3i and x is equal to negative 3i. I've got the plus or minus, so that's how I'm getting the positive version right here. And I'm running out of room. Let me scooch this down a little bit. The negative version. Now, when I'm talking about what these factors are going to look like, when you're looking at my math lab, technically each of these are going to get their own parentheses. If I have 3i, that would be x minus 3i. And if I have negative 3i, that would be x plus 3i. When I write it all factored out, I would get x plus 2, 3x minus 1, x minus 3i, and x plus 3i. Now, it's not very often that you actually have to factor with your i's. So if you're talking about like when it's time to take a test, I would take it as x plus 2, 3x minus 1, and you could use the x squared plus 9 and leave it like that. But when you're talking about my math lab, you do need to make sure that you have it factored with the i's there. And so those are your answers in your factored form. Now, our last problem goes the other way around. We've got our answers and we need to write out our polynomial. So it tells us that we have a degree 4 whose coefficients are real, and then it has zeros 1, 1, and negative 4 plus I. So the thing is, it tells me I have negative 4 plus I right here, but I know that my complex answers have to come in pairs from that conjugate pair theorem. So I also know that negative 4 minus I is an answer. So if I have 1, I know that it's going to be x minus 1. Right here is also going to give me x minus 1. Now, when I come to these, I'm going to do the same thing. When we have our 1, we just flip the sign and make it minus 1. So if I have negative 4 plus I, I'm going to do x. Instead of negative 4, it's going to be plus 4. Instead of plus I, it's going to be minus I. And for this one, same thing. Instead of negative 4, it's going to be plus 4. And instead of minus I, negative I, it's going to be plus I. And then to write my answer, I've got to multiply all of this out, multiply it all together. So the blue over here is nice and easy. It's just foiling, double distributing. So first times first is x squared, outside times outside, negative x, inside times inside, negative x, and then plus 1. So that's going to give me x squared minus 2x plus 1. The right side, the pinks, is where it gets a little trickier because I've got 3 terms in each of those. So when I'm multiplying these, I'm going to start with this x and I'm going to distribute it to everything over here. So x squared plus 4x plus, and I'm going to write it as xi. Then I'm going to do my 4. So 4 times x is 4x. 4 times 4 is 16. And 4 times I is 4i. And then I'm going to do the negative I. So negative I times x, I'm going to write it as minus xi. Negative I times 4 minus 4i. And then negative I squared. I'm going to scoot everything over a little bit. Okay, and we can combine like terms just like we did in our other set of parentheses. So if I'm looking, I've got an x squared. There's nothing to combine with that. I've got a 4x and a 4x, so that's going to give me 8x. The xi and the negative xi cancel out very nicely, just like the 4i and the negative 4i cancel out very nicely. And then I have a 16, but I also have this negative I squared. And if you remember from algebra 1, I squared is negative 1. Sorry, algebra 2. So negative negative 1 becomes plus 1. So I've got 16 and 1, so that's going to be 17. And then I've got to repeat the process and multiply the blue and the pink together. So x squared times x squared is x to the 4th. X squared times 8x is going to give me 8x cubed. And x squared times 17 is 17x squared. Then I'm going to move on to the negative 2x times x squared is negative 2x cubed. Negative 2x times 8x is going to be negative 16x squared. And negative 2x times 17 is negative 34x. And lastly, the 1, that's going to be nice and easy because 1 times anything is just that same thing you started with. So I'm just going to have plus x squared plus 8x and plus 17. I'm going to combine my like terms. So x to the 4th, I don't have anything to combine with, so it's just x to the 4th. Then I've got 8x cubed minus 2x cubed, so that's going to give me plus 6x cubed. Then I've got 17x squared, negative 16x squared, and then another x squared. So I'm going to have plus 2x squared. And then I have negative 34x and 8x, so minus 26x, and the plus 17 on the end. So there's my polynomial equation. There we go. So there's your equation. When you're looking at my math lab, it's going to say like let A be some coefficient. So technically there could be like some coefficient that is multiplied in front of all of this because we don't know like what the y-intercept is or what any other point is, but you don't need to find that. You can just type all of this in and you're good. So that is it for this set of notes. Let me know if you have any questions. Make sure you get started on your assignment that goes with this, and I hope you guys have a good day.